Hello, good afternoon, everyone. My name is Vineet, and today I'll be conducting this session on designing a distributed cache.
So this is what we're going to discuss today. Briefly, we will see some introduction to caching techniques, such as cache aside, write through cache, write back cache, etc. They are not directly related to designing the distributed cache problem, but since we're talking about cache, I thought it's good to introduce them in case the interviewer asks about are you familiar with any of the techniques? And there are some slight considerations that you have to take while designing the system if the interviewers picks a particular strategy, because there are certain nuances, and we will look at those. Then we will discuss the actual problem, designing a distributed cache. And at the end, we will very briefly look at a difference between Memcached and Redis, which are the two popular or two of the few popular caching solutions. There are definitely many more, but these are much more popular than the others. We won't be spending a lot of time on either Memcached or Redis. I will give a few references here and there based on how we are designing our system and whether Redis has that or Memcached has that. And but it's good to know at least the high level differences between those two in case the interviewer goes into a specific solution. Usually in the system design problems, we discourage candidates to talk about specific solution, again, to avoid some going into rabbit hole. And if you're not very sure about how that system is implemented or what are some of the peculiarities of that. However, here, because again, we're talking about like distributed cache, there is a chance that interviewer might want to know whether you are familiar or have you used any of the off-the-shelf solutions. Cool. Can you please raise your hand if this is the first time you're attending any system design or scalable systems related session? If yes, then I will go through the framework. Otherwise, I'll skip this and leave the slide over there for your reference later. But if you have already attended at least some of the SS1, SS2 sessions, then you would know what framework that we propose here. Okay, so far I see only one hand up. So Abhishek, what I'll do is at the end, if you have time, I'll briefly go over that. Or as we are progressing through the framework, I will touch upon these steps. But just in order to save everybody's time, I think I'll just continue with that. All right, so before we talk about distributed cache, let's just briefly see what is a cache. Like, I hope everybody over here has some technical background, so this is nothing new information as such, but just for the sake of kind of completeness, we will start from the basics. Cache, like if you look up Wikipedia, the cache is a hardware or software component that stores some data that you're going to use so that the request for that data can be served faster, mainly because usually your data is stored on either some kind of hard drive or SSDs or databases, and access to that is much slower than if your data was readily available in memory. And distributed cache is just an extension of that concept. Historically, like you would have cache like on the same machine, and actually even going a little beyond that, like cache is it's not, there is no one type of cache, right? There are so many different types. Like even CPU has a cache, L1 cache, L2 cache. Here we are talking about general cache that your application uses, not specifically a database cache or not specifically CPU related cache, but some intermediate store where you can store the information in order to access that quickly and not always go to database, to reduce the traffic to the database and also improve the latency and the throughput. So caches are typically used for that. It's an optimization technique mainly for improving your latency and throughput. By improving a latency, I mean reducing the latency. And another important thing to remember is that they're usually smaller in size. When I say smaller, it's always relative, right? Like compared to the data that you would store in the database. If your data itself is small, then you can actually store everything in cache, but you have to kind of make sure that you are doing the cost benefit analysis because you are improving the speed, but because caches typically rely on in-memory access, so they'll need better and more RAM, and RAM is typically more costly than the cold storage. So you have to see whether is it actually beneficial to store all the data in the RAM or in the cache, or can you actually use Pareto principle where 20% of information could actually serve 80% of your traffic. In that case, you won't have to store everything in cache. So distributed cache, as we just said, it is going beyond that, just having some local memory in your application and kind of extracting that and separating that, putting it in a different set of servers in a distributed fashion. Now, why would we need that? So a couple of reasons. One is your cache requirement is so large that it is not going to fit on one machine. Like every machine will have some kind of upper limit on main memory, right, or RAM. Even if you take very powerful machines like 64 gigs or probably 128 gigs, but it's not gonna be like terabytes of data that you could store in a RAM, or you won't have RAM of that much size. So that's why if your need for cache is large, you need to you cannot just have it on one machine, but you'll have to separate out and distribute among different machines that are dedicated for that cache. Second reason is the local cache availability is tied to the that particular instance, right? So that if the instance is down, whatever you have in the cache, that goes down. So in order to decouple your systems, you can have a cache on a separate machine, so that even if your that app instance is down, like other app instances can still have access to whatever you had stored earlier in the cache. And then lastly, because of this decoupling, you can scale these components separately. So depending on your requirements or depending on needs, you may or may not need to scale your app and cache servers in the same way. For example, if your memory requirement is, or the requirement to store your data in the cache is kind of limited, you may not need to scale your cache significantly, but your throughput is extremely large, so you'll have to scale only the application servers, or vice versa, right? So why unnecessary couple those systems together and make one component dependent on the other? So this is another reason why distributed caches would be useful. There are, however, some side effects, like in system design, most of the problems you will see, like that, it's always about trade-offs, right? There is no one silver bullet. So by decoupling these systems, you are increasing the complexity of the system. Now you have to maintain both applications separately. You'll have to make sure that you have sufficient monitoring, alarming, and hardware provisions on both sides, app and cache. And then also you have higher latency. They are typically pretty fast. Like at the end of the session, we will see some benchmarks for Redis. However, they are not as fast as local memory access, mainly because of having network latency in between. Nikhil is asking, in the foundational videos, if you assume commodity hardware has typical 120 GB RAM, does that number still hold with the latest technology? It depends, Nikhil. Like, I don't think you should kind of look at that number as the guideline as such, because you're right, like technology constantly evolves, and 120 GB RAM is on not all servers may have that, right? Like especially if you're a little tight on budget, then you will probably want to go with servers which have lesser RAM. So in that case, excuse me. In that case, you might need to work with just 32 gigs or 64 gigs RAM. So, and specifically for this problem, that assumption should not matter, because that would be one of the components in deciding how many servers you need, but that can change from application to application. You don't have to, or you should not design your system with certain assumptions that, okay, I'm only going to have 120, or I'm going to have at most 120 gig RAM. Hopefully that answers your question. All right, from system design perspective, it is equally important to remember when not to use cache, because sometimes I've seen students falling into the trap of by default adding a cache component, even if you don't need it. Try not to make your systems unnecessarily complicated, because sometimes interviewers are looking for those signals as well. Are you unnecessarily adding any components just to make your design look more complicated or look more fancy? And they could take that as a red flag. So what are some of the cases when cache is not really that useful, or you should not be using the cache? depending on the use case, right? Like most of these bullet points that you see, they ultimately boil down to the same reason. Depending on the use case, if it makes sense, use it, otherwise don't. So for example, when stale data is not acceptable, every cache will have, as we will see even in the caching techniques, they have the problem of TTL. Like how do you make sure that your data in the cache is always in sync with the database? And if your application requires zero tolerance for any latency, then cache may not be an ideal solution. Like for example, real-time stock prices. If your cache TTL cannot be less than a second, and then if you see that, okay, even a second latency, or latency meaning the stale update or stale nature of the data is going to be a problem, then you cannot afford to use cache in that. If your TTL could be less than that, then sure, use it than that. But that was just an example. I hope you get the point that making sure that the freshness of the data is within the acceptable bounds. The second point is that depending on the traffic pattern, right? If your application is such that, okay, you are sequentially reading the data, and if there is only one application which is just going from, let's say, left to right on a very large file, then the cache is useless because there are not many other components which are trying to read the same data that you already read. So in that case, why unnecessarily introduce the cache? Or if you have millions of users, but their data is personalized, and just because every user does not update their data or access their data frequently. In that case, just having a cache because you have millions of users does not make sense, because one user should not be looking at other users' personal data, right? So you cannot really leverage cache in that. Third reason is, again, simplicity, right? Performance to cost and complexity trade-off. If you think that you are just starting off, you're, let's say, doing some college project, and you don't really care about super optimization. In that case, if you want to save cost, or if you want to reduce the complexity of a system, then you might just implement a local cache using either some of the libraries or implement the cache yourself. So that could be one reason. And then the last is kind of catch-all, like when you don't need to. Just because cache is available to you as a component to use doesn't mean you should use that. Like for example, core workflow of the job scheduler. Like job scheduler is just gonna look at whatever data that you stored in the database, will have some kind of mapping to see when that particular job needs to be executed. But not many people, or not many processes are trying to read the same data that was already read once. So if it doesn't make sense, don't use it. And make sure that you are using those calculated decisions, and or explaining your calculated decisions to the interviewer, that, okay, when are you using the cache, why you should use it, and if you're not using it, also be explicit on why you're not. Nikhil is asking, doesn't write back strategy take care of the stale info in cache? Yes, we will see that, Nikhil, but again, depending on your use case, like write back is also not always silver bullet for that, right? For any kind of solution. So depending on the situation, you will have to make your appropriate choice of the strategy. All right, talking about strategies. So again, this is not necessarily related to the system design problem. This is more, again, of a background information on how the caches could be used. And there could be, this is not like you are using only this strategy independently. You could use a mix of those depending on, again, your use case. So the first and one of the common use case is cache aside. When we say aside, it is basically not in the flow between app and database. So let's say, one second. So if this is your application, and if this is your database, then cache aside, meaning cache sits somewhere separately as a different component. So app can talk to database directly for both reads and writes. And then depending on when we need that data, when they need to read the data, at that time, application is going to check whether data is available in the cache first. If it is not, then application will then go and talk to database, and then retrieve the data and store it in the cache, depending on whatever techniques that you implement. So here, again, the reason it's called cache aside is because cache is not in the flow of, or in between your application and database. This is typically used for read-heavy workloads, because application is always checking in the cache first. And if the data is available, then you don't really need to go to the database to fetch anything. Another advantage of this is it is resilient to cache failures, mainly because now your application has an awareness or understanding of both components, cache and database. So if your cache goes down, it is going to increase the load on the database, but your the whole application is not going to crash unless your database cannot handle that much load. That's a different story. But momentary interruptions in cache, you could the app could gracefully handle that, because it'll if and also if you have coded it appropriately, that if you get an error from cache, then go to the database, not just on cache miss. So it is little more resilient than some of the other techniques that we will see later. And also another advantage is your data models could be different. Like in your database, if you have a table with, let's say, whatever, 5-6 columns, but in your cache, if you just need a key and one of those values, you don't have to replicate the exact structure between your cache and the database. Here, as Nikhil pointed out, actually he talked about the write-through, which we'll see that later. But the issue of inconsistency arise here because the cache does not know what is the correct state of data in the database. The application has to kind of make sure that the cache is updated, because application is checking the cache first. And if the cache never gets updated, that application is always going to have the stale data. So you'll have to rely on some mechanisms like time to live and make sure that you tune those parameters appropriately, so that again, there is enough, the freshness is guaranteed based on your need. It won't be always guaranteed to the nanosecond level, mainly because again, the app is kind of putting the data in the cache. And then if you if there is a cache miss, or if the cache goes down, you'll have higher latency for both read and write, because for both you are relying on the database at that time. Second strategy is called read through. The reason why it is like called read through is because the cache sits in between your database and application. So if this is your app, this is your cache, and this is your database, then your application does not talk to database directly, at least for reading part. It is basically relying on always on cache. But the difference between this and the cache aside is that if there is a cache miss, application is not putting data in cache. Cache is responsible to fetch the data from the database and update itself. So this basically is like very kind of similar technique, because on read, the application is always relying on the cache, like cache first, similar to what we saw earlier. But it adds more complexity on the cache side, because now it needs to be aware of the data model of the database, and also fetching the data whenever there is a cache miss. So what that means is that it can still get inconsistent with the database, because how would the cache know that when the database actually got updated or not? So again, the TTL and other logic comes into picture here. If you have cache crashes, then now, because the application is not talking to database directly, at least on the read part, you have more downtime, because now you have to rely on the cache getting up. Either that's the same server or some other server replacing that, but your calls would be blocked until that time, or they will return an error. The advantage of this, it could simplify your app logic, because now app doesn't have to worry about cache and database separately. It is only looking at cache all the time. Similar to read through, the other way is write through. So this is, in terms of diagram, it will be pretty similar, except the direction of arrows would be different. So here, the app writes to the database always through cache. So that's what I think Nikhil was mentioning before, that here we are solving the issue of consistency, because whenever you're writing, you're always writing to cache first, and then the data is getting written to the database. And this is particularly useful if your traffic pattern is that whatever recent data that you wrote is, there is a higher probability of that data getting read as well. And this is not maybe that useful by itself, but if you combine this with read through, then it becomes really powerful, because again, your app is only talking to cache. Your cache is now consistent with the database, because all the writes are also going through the cache. And then when you're reading, you have the latest information available to you. So that's why pairing this technique with read through would give the best results. And the practical application of this, or one of the applications that uses this technique, is DynamoDB Accelerator. One of the downside is that, again, it is kind of tightly coupled with the database because it needs to know even what to write to the database data model, and then even the connections with the database. Cache needs to be aware of all those things. And then because the data is always going through cache, so first you're updating the cache, then you're updating the database, there is an additional hop. So the latency for writes is higher than if you're not using this technique. But again, depending on your pattern, like if you don't have too many writes, and if your light latency is okay, if you have that little bit more, but then if you're pairing this with read through, your application could get significant like good performance. Like there is a question Ashok is asking, so only difference is who is populating the cache. I think you're referring to read through versus cache aside. And that is one of the main differences. Like another difference is, again, your data model needs to be same, whereas in cache aside, because application owns that, you can put the data however you want. Whereas if your cache sits in the middle of database and application, then the cache needs to be aware of the data model, needs to be aware of the database. Whereas in cache aside, the cache does not need to be aware of the database at all. Ishar is asking, can write through help alone in write heavy workloads? So depending on what write heavy workload you're talking about, Vishal, because the next strategy that we are going to see is write back, or sometimes it's also called write behind. So this is similar to write through. The bigger difference is that, let me just draw that and then hopefully it will be clear. So in write back, the direction of the flow is very similar. The app is writing to cache and then cache is writing to database. The biggest difference is that if every single write that comes through is not written to database immediately. So when the application writes to the cache immediately acknowledges back saying that received. And then after some time, it'll populate it'll insert that information into the database. So to your question about can write through help alone in write heavy workloads, depending on how heavy your workload is, how much data you want to kind of not write to the database, depending on the not just your workload, but how much load database can handle, you can either use write through or write back. Here, the main challenge though is that between the application writes the information in cache and the cache writes to the database, if the cache crashes, then you are going to lose that data. And because it is not happening immediately, like that could happen in write through as well. But again, like in that case, you're writing every single entry in the database before returning an ACK to the application. So the application would know whether it succeeded or not. Whereas here, if you write the data to the cache, send back an acknowledgement, app is going to think that, okay, my data got written. But if the cache goes down, before that the whole batch gets written to the database, whatever data that you had in the cache, you're going to lose that. So depending on what you're okay with, what you want to optimize for, you could either use write through or write back technique for write heavy workloads. Rashmi is asking how pair read through and write through. So your application in that case, like the way you are connecting to the cache, like it will connect to the cache for both reads and writes. So your data will always go through cache and then gets written to the database. And then same thing on the read side, you're not going to read to the database. The application will rely on the cache to return the data. And then cache will need to be aware of the data model, database connection, etc. And then the app does not need to. So in a way, it is kind of simplified the app side, because now app does not need to be aware of both, but then you're adding more complexity and more failure scenarios. Like if the cache is down, then your application cannot then talk to the database directly. Okay, Nikhil is asking, doesn't replication takes care of cache crashing? If you have replication, right? But we are not assuming here that you're always going to have that. And even if you have replication, so it depends on when the replication happens. Like, is the app waiting for the replication if the and then the cache crashes between that time or not? So while designing, like we will see that, okay, we will need to add replication functionality, but it is not by default that every system will have replication, right? If you're using a simple cache and if it is not replicated, then you won't have that. Ashok is asking, isn't writing to cache instead of DB is risky and waiting to DB can guarantee asset compliance? So it depends on your use case, right? So I don't know whether you have already gone through your Uber system design problem and whether the instructor covered that or not. But one use case where you can afford to lose data is, let's say your car is continuously sending updates like every few seconds that, okay, this is my location, this is my location. Now, do you need to persist that location in your database for every single update, right? And maybe not, right? Like you may want to aggregate that data over a minute or so. You don't need to store in the database every single update. So in that case, like write back is useful because you're not hitting the database whenever your car is sending some information. You are storing that temporarily in memory, and then maybe after 1 minute you are updating the database saying that, hey, this is the car's location for this minute. And it doesn't have to be a minute, like even 30 seconds or whatever. The point is, depending on the use case, there could be certain use cases where losing the data is acceptable, and what you're gaining is that you're not continuously bombarding the database for whatever write throughput that you're getting. All right, so these are basically some of the common techniques. Like again, this is not specific to the cache. However, I said that there could be certain things that you may need to remember in your database design, depending if the interviewer asked, like, what technique are you going to use? As we saw, if you're using cache aside, then the cache and database are decoupled, right? They don't need to be aware of each other. But if you're using any other technique, right, write through, write back, read through, then your cache needs to be aware of the database. So you'll have to add some configuration components or some functionality, or at least mention that we will need to have this in the cache so that the cache knows how to talk to the database. But I don't think it is that likely that the interviewer will drill into that. It was more for your information purpose on, depending on what kind of problem you're trying to solve, which strategy works best. If you have that knowledge, I think you can score some additional brownie points. Nikhil is asking, so for Uber vehicle management service, would you prefer right behind? Yes, vehicle management, meaning this specific where the vehicle is updating its location and you are persisting that location, but you don't need to persist every single update. You can aggregate that information over, let's say, a minute or so. In that case, I would prefer write back, because then my cache is acting like the buffer in between where it can handle a lot of throughput, but I don't have to kind of necessarily give all that traffic to the database as well. So for that specific use case, but again, like every application may have many different kind of scenarios where you can use cache for different purpose and you can use different technique. Nikhil is asking, generally we do that via PubSub, right? So in PubSub, like again, depending on, usually like messages are not read, right? When you are publishing something, there are some subscribers which are interested in reading every single message. So that definitely has an application of wherever there are different subscribers, one or more subscribers get reading the data. But here specifically, we were talking about the flow where you are storing the car's location. The car is updating and storing a location. If you're using PubSub here, there will be a subscriber which is constantly fetching whatever data that was published and doing something with that, right? So you can use both. You can have the car publish that, and then your cache could be a subscriber where it is storing the data as an intermediate step, but not every single message that it is getting, the subscriber is getting, that doesn't have to go to the database. The cache can say, okay, I'll write to the database after every minute or so. Even if I miss some updates, that's fine, because I'm gonna know where is the car located in the next minute, and you don't need that much granularity. All right, so now let's start discussing the actual problem, designing a distributed cache. So as you all know, the first step for any problem should be gathering requirements, and the requirements could be of functional and non-functional type. So here our functional requirements are kind of straightforward. You're putting a value in the cache and you're getting a value in the cache. When you're putting, you'll of course need a key and a value. Otherwise, how are you going to identify what value we want to read? For get, you're only requesting, or the input parameter is only key, and the return value you want to get is the value. One thing that I have not specifically called out here that you can clarify with the interviewer is what kind of data types do we need to support. Most likely for an interview, they can say you can start with a simple a key value pair of a data type. Like you can just assume string. Your key is a string and your value is a string. However, there are, and that's how Memcached works. However, Redis supports many different data types. It can support sets, it can support hash tables, strings. So you should clarify with the interviewer, like, do we need to support all of those, or can we support, can we start with just one? And overall, if you're talking about system design, my opinion is that just starting small and supporting the just the strings is enough, because supporting different type will now add more complexity into your app layer handling of how you're handling that data type, but not necessarily the overall system design per se. So, but it still doesn't hurt to ask that question and get clarification. Here we are only going to assume that it is just going to be a string to string key and string value. Few other things that are important in case the interviewer does not give you the functional requirements, then you should ask, in addition to these like put and get, what kind of eviction policy do we need to support? Like one of the standard ones is LRU, and there is also a lead code problem on LRU. So that's what we will be covering today, not coding. Like I don't think anybody would expect you to code in addition to writing the system design. The coding problem itself, I think, is rated as hard. So doing that in addition to solving the system design problem is just not going to be possible in 45 minutes. However, we will see what kind of data structures you need, and that is something that the interviewer can ask you. How will you implement an LRU eviction policy? But that's not the only policy. So you could also ask that, do we need to support any additional ones? Most likely the answer is going to be no. Even if it is like this, there are simple ones such as first in, first out, or last in, first outs, which are even simpler than LRU. But the least frequently used could be a little more tricky. So I will leave that for your homework if you want to think about it. But don't spend too much time on that. It is less likely that interviewer will get into explaining every single eviction policy. Memcached actually only supports LRU, but Redis gives the option of picking which one do you want it. And one of the strategies is also no eviction. So you could also do that. And what it means is if the cache gets full, then that's it. Like you're not going to add any new request. Getting to the cache is going to fail. And whether that is ideal or not, like I don't think so, but there could be some applications where you don't really need more fancy logic from the cache side. But I don't see what you're gaining out of that. But it supports that out of the box. The fourth requirement that we will also see is supporting persistence. So what do we mean by that is, again, are we looking at cache as just the memory, meaning that if the cache is down, we lose the data? Or do we also provide a functionality where we can persist that data onto some cold storage? And in this case, we are assuming that we are supporting that. Not everybody does that. That's another difference between Memcached and cache. Like Memcached does not have persistence mechanism, whereas Redis does. And then lastly, we don't have to worry about security. Even if interviewers does not explicitly mention security, you can say that at this moment, I'm not considering security. But even if you do, it is going to, the architectural wise, there's probably not going to be that much difference. It is like when you're storing the data, you'll have to store it encrypted. And then when you are returning the data, you'll have to decrypt and return. So that adds the complexity on the app layer, but not necessarily the overall design of the system. And then the non-functional requirements, we can assume that the system is to be scalable, available, high performance, etc. We will talk about the performance benchmarks. It is kind of, I don't think anybody would expect, like when you say high performance, like define exactly how much traffic can you support and how much latency, because as we will see later, there are multiple factors that will affect that. But there are still certain answers that you could give to communicate that how you will what kind of techniques you will use to ensure high performance, and then what will you do to measure that, and what can you do to tweak that to see that whether you can achieve even better performance or not.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today